These three minerals have something in common. This guy right here is muscovite, this guy here is lepidolite, and this here is graphite. Okay, all three of these are examples of covalent networks, okay, or covalent network solids, or network covalent solids. We've got basically atoms that repeatedly covalently bond to each other, so we end up with no molecules, just very large repeating structures. This makes them stronger than most typical covalent compounds and covalent molecules, gives them higher melting and boiling points and things like that. But what's interesting about these specific examples is how they're held together, because the whole thing isn't covalently bonded. We actually have sheets that you can see especially well in this piece right here. Okay, this flakes off in sheets like this. I didn't slice this in a very thin sheet. And I might be able to break a piece off of here. Let's see if I can get underneath it with my fingernail. Ooh, I think I almost got it. If I get this corner here. These sheets stack on top of each other, kind of like this. This is an example for graphite. Okay, we actually call each layer graphene, and this is big in kind of the tech industry world right now for its electrical conductivity and some other properties. It might be good for batteries and things like that. But each layer of these covalently bonded atoms is not bonded together. So this layer is independent of this covalent network layer, which is independent of this covalent network layer, and on and on. So they do stack and they do attract each other to a certain extent, but they don't hold together with covalent bonds from layer to layer. Instead, they're attracting with dispersion forces, or London forces, or instantaneous dipole-induced dipole forces. Okay? As a result, you get a fairly strong structure within the sheet, but between sheets it comes off pretty thin and pretty neatly. We can easily kind of sever these intermolecular attractions in between each sheet, and they can just slide off of each other. This makes graphite great to write with because it really comes off easily. You can see it just marked onto my thumb there. Okay, so you can use it for pencil lead. You can really also see the sheets come off nicely in this piece of lepidolite. If I can just get underneath this with my fingernail, I can just flake some sheets off right there. Okay, muscovite and similar materials like this are often used for electronics, all kinds of stuff. But this ability to flake off in these thin sheets and layers is all due to the fact that these sheets are only held together by intermolecular forces, and by dispersion forces specifically, not by actual bonds. Okay, the sheet as a whole is fairly, tough. It's not, unbreakable, but it can bend a little bit, it can flex a little bit. But I can break off individual sheets pretty easily by severing those intermolecular forces rather than fighting against the covalent bonds within the layer. The dispersion forces that hold together these sheets of these minerals really goes to show that intermolecular forces can add up. It's not just the strength of the individual attraction from one partial positive to partial negative, from a dipole to a dipole or a temporary dipole to whatever. It's also about how many attractions you have. So having a whole bunch of surface area for these attractions to happen on from sheet to sheet gives you a lot of area to have an attraction on, and therefore you get some relatively durable sheets here that I can't really pry apart from each other. Okay, once maybe I got underneath it, I could get a little bit better, but otherwise this holds together pretty well. Okay, so intermolecular forces can work by strength in numbers, not just by the strength of the individual attractions. And we're going to see that with these examples of hydrocarbons here. On this chart, we're going to compare some hydrocarbons, which are just compounds that are only made of carbon and hydrogen. Along the left side, we have the names of these hydrocarbons: methane, ethane, propane, butane, pentane, hexane, heptane, and octane. And as we go down from each one, we're adding one carbon atom and two hydrogen atoms. So methane is CH4, ethane is C2H6, propane is C3H8, and on and on and on. Now, we also have here the boiling points listed and the densities. So looking at the densities first, there isn't a huge difference from comparing methane to octane or pentane or things like that. These are all fairly close together, and these are the densities measured when they're liquids. So that much hasn't changed. When we put the molecules close enough together to roll around past each other, they're about as closely packed, comparing one to another. But we do see a big difference in the boiling points. Okay, as we go down, we go from boiling points in the negatives, which means at room temperature they are very much a gas, and even if we got methane down to like negative 150 degrees Celsius, it would still remain a gas. We'd have to get it down below negative 164 degrees Celsius to get it to be a liquid. Okay, we see kind of a divide here from butane to pentane, where we start dealing with compounds, hydrocarbons, that are a liquid at room temperature. So above here, at room temperature, these are gases, and below here, these are liquids at room temperature. Okay, just kind of for reference, 36.1 Celsius is about 96 or 97 degrees Fahrenheit. Okay, so at that temperature, pentane would boil into a liquid. Okay, boil into a gas. Butane's negative 0.5 Celsius is somewhere around 32 Fahrenheit. So around the usual freezing temperatures for water, butane would boil from a liquid into a gas. So at room temperature, we're kind of laying right in between here. So I've got some samples of these. I've got propane, I've got butane, and I've got pentane and hexane. These four here. Okay, we're going to compare them and see how how their structure can maybe tell us something about why they're a gas or a liquid, and how that relies on the intermolecular forces between them. So here are my actual samples of propane. This is butane, this is pentane, and this is hexane. All right. Now, you may be fooled if you take a jug of propane and kind of shake it. You might hear a little bit of liquid in there. And same with butane. If you listen, you can kind of hear something sloshing around in there. And they are liquids at the time. But because they're usually gases at room temperature, in order to store them easier and to transport them easier, to be able to hold larger quantities, we pressurize them so much we condense them into a liquid. So do not be fooled. These would usually be gases at room temperature. If you need to convince yourself otherwise, propane is one of the main components of natural gas. If you've got a gas stove or a gas grill, that's the gas that's coming out. So hopefully your stove or oven or grill is not shooting out liquid to start your fire. For butane, that's the typical fuel used for lighters, like the small little Zippo lighters, or the ones that kind of have the long handle that for like lighting candles and things like that. So again, you're using the gas to light those. Okay, so these are usually gases at room temperature. Okay, our pentane here is a liquid. I can pick this up and kind of shake it around, and you can hopefully see it's a dark bottle. Let me see if I can. Oh, it's at the top there. So if you watch the top there, there's our liquid. Okay, and our hexane, bottomless bottle here. Again, a liquid. These are not pressurized; they're just ordinary bottles. Opened them up earlier to check them out. It doesn't really smell very good, so I closed them. Okay, so what do these look like as molecules? Well, propane looks something like this. Again, it's a hydrocarbon, only C's and H's. So this is a fairly nonpolar molecule. We don't really have a lot of areas for partial charge, for a little bit more partially positive here, partially negative there. This shares electrons pretty well across the carbons and the hydrogen, so this is a fairly nonpolar molecule. Therefore, any attraction between a molecule of propane here and another molecule of propane over here is going to be a dispersion force. It's an instantaneous dipole induced dipole force, or a London force. Okay, so a weak intermolecular force. All right, well, what does butane look like? Well, again, butane is basically just one more of these tacked on here. Okay, so this is butane. Looks basically the same, also nonpolar. It's just kind of one bit longer in this chain. Okay, so what about pentane? Pentane, again, takes another one of these and swaps it for one of these guys. So we get something like that. Okay, 1, 2, 3, 4, 5 carbons right there. Still nonpolar overall. And then hexane, again, loses one of these. That, and that, and one more. And this is hexane. Okay, again, nonpolar. The only thing that has changed is the chain of this molecule, the number of carbons and hydrogens, has increased. We have just kind of made the molecule longer. And that's really the only difference. Okay, going from propane to butane to pentane to hexane, the only difference is our molecule gets longer. So how does that make a difference in whether it's a gas or a liquid at room temperature? Well, the simple option would be to say, well, it's heavier. Okay, you got more atoms in there, so it's a heavier molecule, so it's harder to get it moving. Okay, and yeah, that's a good start, but chemically it's not really enough to make a good point. There are a couple examples you can go look up and find strange differences, like the molar mass of table salt, sodium chloride, is basically the same as butane's molar mass. So, I mean, they're about the same size, but butane is a gas, salt is a solid. So the molar mass and kind of heaviness aspect of it isn't a real good way to kind of argue that this is a gas or a liquid at room temperature. Instead, we have to think about the intermolecular forces. So what would make the intermolecular forces kind of stronger between something with 6 carbons compared to something with 3 carbons? Well, dispersion forces are all about getting kind of the electron cloud to be pushed around. We get a little bit of partial positive here, a little bit of partial negative there, and then we have an attraction that results from that induced dipole, okay, and the instantaneous temporary dipole that starts out. Okay, this effect can therefore be maximized if you have more molecule and more electron cloud to push on. Well, let's see if I can get this guy back together. Yeah, okay. So if you've got a bigger molecule, you've got more places to push on the electron cloud, more surface area to push on the electron cloud, and to therefore polarize. Okay, a bigger electron cloud means it's able to be polarized more. It's more polarizable. So the electron cloud of this entire molecule can be polarized better. Therefore, you have a bigger difference in your partial positives and partial negatives than something that's a smaller molecule, like a chunk of this. Okay, so more polarizable, there's a bigger difference in your partial positives and partial negatives. That means a stronger attraction between, the partial positive of one molecule and the partial negative of another molecule. Okay, stronger attractions means things are held more tightly together, which means they're more likely to kind of hold together as a liquid rather than a gas. So the more CH2s we kind of add on to this thing to make the chain longer, the more surface area we have, the more electron cloud we have to polarize. Therefore, the stronger the intermolecular forces that kind of attract and hold one molecule to another, which means things are more likely to be more liquid-like rather than gas-like. Okay, so surface area is huge for especially dispersion forces. Even though the intermolecular force itself, the dispersion force, is very weak, kind of adding a bunch of them together and having strength in numbers can make a huge difference. And it's evident in the difference between these substances and their boiling points.